Hello everybody, welcome back to another video lecture for Logic 1000. Today we are going to just work through some more examples of using the long truth table method for checking arguments for validity or invalidity. Now, one thing I've done here, really just for the sake of time, so I'll try to keep the video to about 50 minutes. One thing that I'm just skipping right over is the natural language component of the argument. Taking it in normal English, trying to convert that into simple statements and then symbolize the relationships between the simple statements. Really just doing that for the sake of time here. When it comes to the exam, there will be some questions about translation. There will also be some questions just like this, where I just give you the symbolic representation and ask you to check it for validity or invalidity. So expect to see some questions like this as well, where you're just dealing with the argument while it's already in its symbolic form. And look, an argument like the first one we're going to look at. So I've cooked up, I think, 6 different examples here in this Word document. I'm just going to work through them. I just came up with these off the top of my head. Like I said in, I believe, the previous video, really what we're doing is just checking certain argumentative patterns for validity or invalidity. And so in this instance, in the first one, what do we have? 2 premises and a conclusion. Premise 1, if P is true, then Q is true. Premise 2, if Q is true, then R is true. Conclusion is R, right? We're going to see if this is valid or invalid. So look, it could be something, the contents of the statements could be anything. If it's sunny, then I'll go for a walk. And if I'll go for a walk, then I'm going to get some exercise. Therefore, I'm going to get some exercise. There, that could be one set of statements, one way of taking this argument form and putting it back into natural language. But it could be something else too, depending on what P and Q and R mean, right? It could be, if I have some apple crumble today, then I'm going to eat some ice cream. And if I eat some ice cream, then I'm going to have a lot of sugar. So I'm going to have a lot of sugar today. Or it could be any of these things. So I'm skipping over the natural language component of it. I hope that doesn't cause too much confusion. But like I said, the relationships we're looking at here, the logical relationships, really apply to any set of simple statements we might want to stick in to the values of P and Q and R here. And the same goes for everything else. So we just are going to work through what we've already looked at. So we need a truth table to represent this. So if we think about using the long truth table method, the first step of that is to make a truth table that represents the whole argument. Now, to do that, we've got to go back to chapter 2. We got to take those 7 steps from chapter 2. What were those? For at least this one, I'll work through those steps in order. So first we have to identify how many simple statements we have in the argument. Well, let's see, how many letters do we have? That's really the question. P, Q, R. So we have 3 simple statements. Okay, so now we need to stick those in a header row. We need a column for each simple statement in the argument. So it's going to be P, Q, and R, right? Center those, just like how it looks. We'll put those in bold as well. So we got P, Q, and R. So that's step 2. Put a different column in the header row for each simple statement. We also need another column for each complex statement in the argument. So if we look back, we've got P1, P2, we've got the conclusion. The conclusion is just R, right? The conclusion is just a simple statement, so that's already represented in one of our columns. We're going to need a column for if P then Q and a column for if Q then R. So we need 2 more columns in our header row. Right? One for P to Q, one for Q to R. Look at that. Step 4 is to label the premises and the conclusion in the header row. So premise 1 is if P then Q, premise 2 is if Q then R, and the conclusion is just R. So there, we've got our header row. And I'm going to go ahead and stick in a little bit of color just to make it look nice. I like that light blue, whatever that is. Okay, now we need to, step 5, this is again from chapter 2, just in constructing a truth table. Step 5 is to figure out how many rows we need. We need a number of rows that's equal to 2 to the power of n, where n is the number of simple statements. We have 3 simple statements, 3 letters, P, Q, and R. So that means 2 to the power of 3, and that is 8. Remember, anytime you have 3 simple statements, you need 8 rows. So we'll just add those now. 1, 2, 3, 4, 5, 6, 7, 8. Oh, now all my rows are blue. I don't want that. There. Good. Okay. Now, that's step 5. So we only have 2 steps left from chapter 2 in constructing our truth table. So first we have to fill in the values, the truth values for our simple statements, in this case P, Q, and R. Remember, there's those 2 methods to do it. I'll just use the first method for this table. I'll try to just alternate between them as I work through these questions, just to show you those 2 different ways of doing it. So we've got, we'll start at the left, which means we do half true and half false. So true, 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 false, 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 false. Because of course we've got 8 rows, so that means 4 true to start with, followed by 4 false. When we move over to Q, we do half as many at a time, but we still fill in the whole column. So true, true, false, false, true, true, false, false. We'll zoom in a little bit here just so it's a little bit larger, a little bit clearer, I hope. And then finally, in our last simple statement column, we always just alternate between true and false. So it's true in one row, false in the next, and we just repeat that pattern the whole way through. There, we're done step 6 of constructing our truth table. We've got our simple statement columns. We have our 8 rows that represent all of the possible combinations of those, the truth or falsity of those simple statements. So in the first row, they're all true. In the last row, they're all false. And if you look at every row in between, it's a different combination of how they can be true or false. So our last step, step 7, in constructing our truth table, is just to fill in the truth values of the complex statements. So we'll just go in order here. So if P, then Q. Remember, that's only false when the antecedent is true and the consequent is false. All that statement is really telling us is if P is true, then Q must be true as well. It's just saying it's not the case that P will be true when Q is false. When P is false, it's true. It's just not telling us about what happens when P is false, about whether or not Q will be true or false. And when they're both true, then, well, the statement's really telling us what's happening, right? If P is true and then Q is true, the statement if P is true then Q is true is going to be true. So really all we're looking for are instances where P is true and Q is false. Then the statement will be false, otherwise it's true. So in the first row, both P and Q are true, so their complex statement if P then Q is true. Second row, we see the same pattern. They're both true again. So the statement's true. In the third row, P is true but Q is false. That's exactly what we're looking for when if P then Q is false. So we know it's false there. In the third row, we've got the same thing. P is true but Q is false, which means if P then Q is false. And we can look very easily, we see in these last 4 rows, P is true, or P is false in these last 4 rows. Whenever P is false, an implication statement that starts just with P, if P is the antecedent and it's false, then the statement is always true. And again, if that seems confusing, go back to chapter 3 where we talk about the implication statement to see why that's the case. So there. We've got our column filled in. We see that if P then Q is only false twice, otherwise it's true. Now we'll move over to if Q then R. Same thing. What we're really looking for is a situation where Q is true and R is false. If we find that, then the statement is false. If we don't find that, then the implication statement is true. So the implication statement is true when Q and R are both true. It's true when Q is false, no matter whether or not R is true or false. If Q then R is only false when Q is true and R is false. So let's look through. So in this first row, Q is true, R is true. So if Q then R is true. Second row, Q is true but R is false. So if Q then R is false. In the third and fourth rows, we see that Q is false here. Remember, whenever the antecedent is false, the implication statement is true. So we've got true, true again. Well, don't need 2 truths there. Okay, moving down into the next row, row 5. They're both true, so the implication statement's true. Now here's the pattern. We've got Q being true while R is false again, so that makes the statement false. And then in the last 2 rows, Q is false, so the statement is true. Look at that. So we filled in our table. We finished all 7 steps from chapter 2. Now, we need to move on to the next step of the long truth table method, which is to identify the rows where the conclusion is false. So to do that, we pick out the column that represents the conclusion. The conclusion of the argument is R, right? That's what we had up here to start with. So we need this column that represents that conclusion. Of course, we labeled it with C for conclusion before. Now we just need the rows. We need to identify and check the rows where a conclusion is false. So I'll go ahead and I'll shade them again. It's, row 2, row 4, row 6, and row 8. Now, what we want to find now, we need to check the truth of the premises. This is really the last step in the long truth table method. We need to check whether or not we can find a row that has a false conclusion and all true premises. If we can find that row, this argument is invalid. But if every time the conclusion is false, at least one premise is false, then the argument is valid. And remember, this is all because in a valid deductive argument, the truth of the premises guarantees the truth of the conclusion. What does that mean? That means if the conclusion is false, at least one of the premises has to be false. If the conclusion is false while all the premises are true, then we don't have that guarantee that the truth of the premises guarantees the truth of the conclusion. So we're just trying to see if the guarantee holds up or not. So let's just go ahead and check row by row. So we'll start in row 2 and we'll work our way down. We just ignore rows 1, 3, 5, and 7 because the conclusion is true. So we just look through. What do we have? Well, in this second row, we've got premise 1 is true, but then premise 2 is false. And I'm shading them. You don't have to shade them when you're doing your own work. I'm just doing that for demonstrative purposes here. So we've got one true premise, but a false premise. So this row doesn't show us invalidity. Right? That's really what we're looking for. We're either looking for invalidity or checking every row where we might find invalidity. Right? And once we found invalidity, if we find a row where all the premises are true, the conclusion is false, we can just stop and really point it out. Now, that said, we should keep going just to show exhaustively how often it does, and that's something I will ask you to do on the exam. We'll say, okay, check this argument for validity or invalidity using the long truth table method, what we're doing here. Identify which rows, if any, show us that the argument is invalid. Okay, so let's move on to row 4. And that row, premise 1 is false, premise 2 is true. Here we go. Look at the right shade of green. Right? So here again, conclusion is false, but we have at least one false premise, so we haven't found invalidity yet. Great. So let's just move on to row 6. Here we've got, premise 1 is true again, but premise 2 is false. So again, we haven't found invalidity yet. So let's check row 8. Oh, goodness. Row 8, this is our winner. Look at this. Premise 1 is true, and premise 2 is true, while the conclusion is false. So, what does that show us? That shows us, sorry, I'm sort of skipping around there. I've just got a little formatting issue. This argument is invalid. The conclusion is false in row 8, while all the premises are true. If all the premises are true, the conclusion is false, that shows us the argument is invalid. And that's exactly what we see here, right? In row 8, both premises are true, but the conclusion is false. So what's going on here? Why is that the case? Well, we can see from the truth table, both of our implication statements are true, but the conclusion's false. So why did that happen? Because this almost seems like a valid argument. If P then Q, if Q then R, so R. It would be valid if we also had P. If P were asserted as a premise, this argument would be valid. So look, let's go back to one of the example natural language versions of the argument I gave. I think this is what it was, or at least it's pretty close. If we fill in some information for P, Q, and R, we can think about this. So look, if it's sunny today, then I'll go for a walk. If I go for a walk, then I'll get some exercise. So I'll get some exercise. That conclusion, I'll get some exercise, only follows if it's actually sunny today. Right? Because P1 is saying, if it's sunny, then I'll go for a walk. P2 is saying, if I go for a walk, then I'll get some exercise. The conclusion is saying, so I'll get some exercise. That conclusion that I'll get the exercise only follows if it's actually sunny. All premise 1 said was, if it's sunny, then I'll go for a walk. It didn't actually say that it's sunny out. It's just telling us what is going to follow if it's true that it's sunny. But the statement, if it's sunny, then I'll go for a walk, doesn't actually tell us that it's sunny. It just tells us what will follow if it's sunny. Now, this is something to note when you're thinking about the last homework assignment, finding a deductive argument and putting it in this form and testing it this way. Often, conversationally, we will leave out parts of an argument, right? Those parts are missing or unstated. We were looking at this when we were going through the Hughes and Lavery material. Often people will say something like, look, say I'm looking out the window and it's nice and sunny, and they say, well, if it's sunny, I guess I'll go for a walk, so I'll go for a walk, right? Now, of course, I didn't say it's sunny, but maybe we can see it. Maybe I assume you know it's sunny, right? Or something like that. We do this kind of thing all the time. Or, you'll look out and you'll say, well, if it's sunny, I'll go for a walk, and I see it's sunny out, so I'll go get my shoes on. Now, we didn't actually say that we'll go for a walk, but the conclusion is going unstated. It seems too obvious to be worth saying. So often there will be these missing parts, especially in a deductive argument. Another common deductive argument form is, either this or that, not one of them, so the other one. Right? You say, and this, you'll probably have to make an exclusive disjunction if that's the argument form, right? But it'd be something like, oh, either I'll go for a walk today or I won't go for a walk today. So I guess I'm, oh, and I'm going to go for a walk today. So it's not the case that I'm not going for a walk, right? It's false that I didn't go, right? Which really amounts to I did go. So maybe that's not a great example. But look, say something like, well, would be a good one. Either I'll make another logic video today or I won't, right? And if I don't have enough time, then I'm not going to make another video. And I don't have enough time, right? So what? What does that all add up to? Well, it adds up to I'm not going to make another logic video today. So think about the sorts of patterns you might see here, and keep in mind that you're going to have some missing parts to arguments. Particularly deductive arguments can have this sort of feature, right? People just don't explicitly say everything that's part of it. Okay, let's move on to our next example. So that's it. We're done this example, right? This is really what I'm asking you to do, and I'm asking you to use the long truth table technique. For the purpose of the assignment, you have to find something in natural language and then translate it over into the symbolic form. But then once you have the symbolic form, which is really what's going on here, this is our symbolic representation of the argument, we then make the table. We check those relevant rows to see if we can find a row that shows us invalidity. If we find at least one row that shows us invalidity, the argument is invalid, right? And this is really the last part, just explaining what your table's showing you. The argument is invalid. In this case, why? Because we've got a row where all the premises are true and the conclusion is false. If we couldn't find that, right, if every time the conclusion is false, there's at least one premise true, then we could just say that the argument is valid because in every row where the conclusion is false, then at least one premise is false as well. Okay, so moving on. If not F, or premise 1, not F, whatever that is, right? Premise 2, if N is true, then F is true. Conclusion, not N. And again, these could stand for anything, right? N and F. What? If it's nighttime, then there's fireworks going off, right? There's no fireworks going off, so it's not nighttime. Now, presumably, if we wanted this to be accurate to the world, it'd probably be something like, if it's nighttime on Canada Day or something, right? Or some holiday where fireworks go off, right? If it's nighttime on Canada Day, then there will be fireworks, or something like that. It's not the case there will be fireworks. So it's not the case that it's night on Canada Day or something. Okay, so look, again, we're going to make our truth table. So how many simple statements do we have? This time actually just 2, just N and F. So we'll start with 2 columns, right? One for F, one for N, one for F. Okay, there are simple statements. What else do we need? Well, we need one for every complex statement. How many do we have? We actually have 3 complex statements in this argument. We have not F, not N, and if N then F. So let's go ahead and put in 3 more columns, one for not F, one for not N, and one for if N then F. Good. One suggestion, so this isn't absolutely necessary when you are constructing tables, but I think it's helpful. Try to always increase the complexity of the statements as you move to the right. The complex statement, not F or not N, a complex statement that's just a negation of a simple statement, is really the simplest kind of complex statement there can be, because the truth value of that statement is really just the opposite of the truth value of the simple statement that it's negating. If N then F, it's a little bit more complex because it depends on the truth values of both of those. Now for this argument, it really doesn't matter because the implication statement I have to the far right doesn't actually take one of the negations as the antecedent or consequent. So it doesn't really matter what order I have them in, just in terms of getting it in the increasing complexity as we move to the right. But it's just as a general tip, if you have negated simple statements, start with your simple statements on columns to the left, then move into negated simple statements, and then move on to more complex statements to the right. Okay, so we've done this. We've got the basic parts of our header row. I need to identify the premises and the conclusions. So premise 1 is not F. Premise 2 is if N then F. Conclusion is not N. Good. I'll go ahead and stick a little bit of coloring up there. Okay, also make that bold. So we've got our header row. We've got the argument represented in these 3 columns. We've got a different column for each simple statement and each complex statement. Now, of course, we need to figure out the number of rows we need. In this case, it's only 4 rows. Why? Because we only have 2 simple statements. We fill those in. I'll use the second method. So we'll start with the rightmost simple statement, the last simple statement. We just go true, false, true, false. Oh, I've still got bold on here. And then we move a column to the left and we go true, true, false, false. Look at that. So we filled in our simple statements. We've got our header row done. Now all we have to do here is fill in the truth values for our complex statements. Like I already said, the negation of a simple statement just is the opposite truth value of the simple statement in a given row. So in the first row, F is true, so not F is false. In the second row, F is false, so not F is true. Third row, F is true, so not F is false. Fourth row, F is false, so not F is true. Same thing for not N. And so look, the first 2 rows, N is true, so not N is false. Last 2 rows, N is false, so not N is true. Then we've got our very last column, if N then F. Here again, that's only going to be false when N is true, but F is false. That happens only in the second row. So really what we have, if you just ignored the third and fourth columns, if you just got rid of those, you just ignored, you pretend like they weren't there. In fact, I'll delete them for a second just to show this. Even though we've got columns that separate the implication statement over here from the simple statements that make it up, what we really have going on in these 3 columns is just that basic truth table for the implication statement. First column, or the first row, both simple statements are true, so the complex statement is true. The second row, antecedent is true, consequent is false, so it's going to be false. And then we've got the antecedent false in the last 2 rows, with the consequent being true and false, which makes the statement true in both. We want to put these other values back in here. We have true, false, true, true. Just like a normal implication statement truth table that deals with 2 simple statements. Okay, so we've identified all this. Now we have to figure out where is the conclusion false. So the conclusion's not N, and we see here it's false in the first 2 rows. So now we just need to check the truth of the premises. Is this a valid argument or not? Well, look, in the first row, premise 1 is false, while premise 2 is true. Okay, so far so good. That doesn't show us the argument's invalid yet, right? Conclusion's false, but at least one premise is false. That's good. In row 2, conclusion's false again. Premise 1 is true, but premise 2 is false. That's it. Right? We're done. So last thing to do, turn off my caps lock. This argument is valid because in every row the conclusion is false. I want to put in here 1 and 2, at least one. This is false. There. That's it. We're done. We've checked this argument for validity. This is another common argumentative pattern. So in this one, what we have really is an implication statement telling us if one thing's true, this other thing is going to have to be true. But the thing that follows isn't true. It's false. So the first thing must be false as well. So look, this could be almost anything. We could say something like, okay, so what, we need to fill in values for f and n. Okay, F, my fingers are tired from typing all day, say. So F is, Carl's fingers are tired. N is, it's nighttime. So look, premise 1, not F. It's not true that Carl's fingers are tired. Right? Premise 2, if it's nighttime, then Carl's fingers are tired. Now, what's really going on here? If it's nighttime, then we're saying it has to be the case my fingers are tired. Anytime it's nighttime, my fingers are tired. Right? But my fingers aren't tired. That must mean it's not nighttime yet, because premise 2 is saying if it's nighttime, then 100% Carl's fingers will have to be tired, right? It's not probably tired, it's not might be tired, they are tired. And if my fingers aren't tired, that means it must not be nighttime, right? To assert the two premises and then deny the conclusion would be to contradict ourselves in this case. Now, that said, it's not always the case my fingers are tired at nighttime. I was just, when I'm making these examples, I'm just sticking together operators and letters. That might seem really haphazard. In some ways it is. It's in part to keep me honest. What I've been teaching you here, this way of approaching arguments by representing them this kind of way, sticking them on a truth table, it doesn't matter what the argumentative pattern is. It doesn't matter what the letters are. It doesn't matter what the statements are. All that matters is how they fit together. So any argument of this pattern, right? Not some statement, not F, not A, B, C, D, P, Q, not whatever it is. Any argumentative pattern that says not this thing, right? Not A if B then A, so not B. Or we can replace, as long as we consistently replace the letters. You could replace F with anything, you could replace N with anything. Those letters could represent any statements at all. And as long as the argument has this pattern, it's a valid argument. Okay, let's move on to our next example here. All right, this one's a little bit more complex. So C as long as B, right? Or C if and only if B. So we have a biconditional statement this time. That's the first premise. Second premise, not B or T. Okay, so either not B is true or T is true, or both not B and T is true. That's what the second one's telling us. Premise 3 just tells us C is true. Conclusion, T. This argument is a little less straightforward. Right? Those first two arguments, you could probably look at them, and especially once you get familiar with this kind of logical system, becomes a lot easier to start recognizing certain patterns, how you can make certain moves in logic. So we look at this one, it's a little more complex, right? The first premise, C is true if and only if B is true. So either they're both true or both false. The second premise, either not B is true or T is true, or both of those are true. Third premise, C is true. Conclusion, T is true. Valid argument? Maybe, maybe not. So let's make our table and find out. So First, how many simple statements do we have? We have C, we have B, we've got T. Okay, that's it. We've got 3 simple statements again. So we'll start with our 3 columns. So we've got 1 for C, 1 for B, 1 for T. How many complex statements? Well, we've got the biconditional, we've got the disjunction, and we also have the negation. We've got just not B. So we'll put in 3 more columns, 1 for each. We'll put not B here. Like I said, negations are really easy to deal with. Let's put B or not B or T right here, given that we have not B right beside it. And then let's put the biconditional at the end. So we've got C, and this is where you might have to, I'm just moving, go to insert, use the symbol. You can go find it in more symbols, but this left-right arrow for the biconditional. There's also keyboard shortcuts you can look up to find it. Or like I said, you can just put in 2 arrows, just trying to make them with hyphens and this sort of thing. So, all right, so we got a biconditional. Now we need to label our premises in the header row. So this is premise 1. This is premise 2. Premise 3 is actually just C. The conclusion was T. There we go. And of course, one thing to keep in mind, you can have C as a letter, and that's something different from denoting the conclusion with the C in parentheses. Okay, now how many rows do we need in addition to the header row? Well, we've got 3 simple statements, so that means we need 8. 1, 2, 3, 4, 5, 6, 7, 8. As usual, I'll add a little bit of coloring just to jazz things up a little bit. Oh, why don't we go with some kind of whatever that is. Okay, now we need to fill in simple statements. True, 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 false, 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 right? Half true and half false. We've got 8 rows, 4 true, 4 false. We've got true, true, false, false, true, true, false, false. And then true, false, true, false, true, false, true, false. Right, we alternate in the last row. Okay, not B. All we need to do is compare the truth values in the column representing B and just reverse them. So in the first 2 rows, B is true, so not B is false. Next 2 rows, B is false, so not B is true. Same pattern, B is true, so this is false, and then false, so true in the last 2 rows. All right, the disjunction. Either not B or T or both, because it's an inclusive disjunction, right? That disjunction tells us that at least one of them is true, but it could be both of them is true. Okay, so to figure out whether or not that disjunction is true, we need to take a look at the 2 columns that represent the disjuncts, not B and T. So the complex statement, either not B or T, is only false when they're both false. So that's really what we're looking for. So in the first row, at least one of them is true. T is true, so the disjunction is true. Second row, they're both false in the second row, so the disjunction is false. Third row, they're both true, so the disjunction is true. Not B is true in this row, so it's true. T is true again. They're both false, so it's false. And then here they're true again. And then lastly, at least one of them is true, so the disjunction is true. Look at that. So we've got it false in row 2 and row, 6. Otherwise, it's true. Now the biconditional. Remember, the biconditional is true so long as both of the connected logical units are either true or false. So the biconditional is just telling us it can't be the case that one of them is true while the other one's false, or vice versa. Okay, so the biconditional. We need to take a look at the columns for C and B, because those are the logical units, the biconditional, C if and only if B is trying to connect. And we're just trying to look for an instance where they're, if they're both true or both false, the biconditional is true. If one is true while the other one's false, then the biconditional is false. So we'll just start in the first row here. Both of them are true, so the biconditional is true. Second row, they're both true, so the biconditional is true. Third row, C is true while B is false. Biconditional is false. Same thing in the fourth row, so biconditional is false. Fifth row, C is false while B is true. so the biconditional is false. Fifth row, same thing. Sixth row, or seventh row, I'm sorry. They're both false, so the biconditional is true because the biconditional is just telling us they're both true or false at the same time. And in the eighth row, they're both false, so the biconditional is true. Okay, good. Now we need to identify the rows where the conclusion's false. So that's rows 2. That doesn't look quite as nice. Just trying to do something other than use the fill, but all right. So row 2, the conclusion's false. Remember, our conclusion in this argument is t, so that's why we're interested in this column. So we've got row 2, row 4, row 6, and row 8, where the conclusion is false. Great, now we just need to check the premises. This time we have 3 premises to check instead of 2. So let's just go from left to right. Instead of going premise 1, premise 2, premise 3, I'm just going to start in the leftmost column, right? C, this is a premise, so we'll check that column first, and then we'll go over and check the other 2. And in fact, I want to do something a little bit unusual this time. Instead of sort of doing each row at a time, I'm going to do each column at a time. I'm only really doing that because I'm highlighting. Right? I'm just sort of going through and sort of showing, okay, we've got true, true, because the highlighting makes it sort of easy to see. And like I've mentioned in the past, really, ultimately what matters is the end product here. If you follow the steps outlined in the text and the lectures here, you're always going to find, you get the same results. You'll get the right result as long as you haven't made a misstep along the way. Now, you can sort of mix up some of the steps the way I'm doing here if you want to, at least some of the time. But doing that, you've got to sort of keep in mind that you're getting everything done correctly by the end of it. So I'm sort of taking a bit of a shortcut here. I've got what I want, so I've done all my coloring. Now we still need to actually read through each row though. So even though I've done it this way just to do the coloring because it's been easy for me to look at it that way, we still need to read across each row. So in row 2, F is false. We've got 2 true premises, but at least premise 2 is false. So that row doesn't show us invalidity. Row 4, same thing. The conclusion's false, right? It must be, that's what we're interested in. We've got premise 3 is true, premise 2 is true, but premise 1 is false. So we're still valid, we're still doing well. Row 6. Row 6, look at this. All of the premises are false in that row. Isn't that interesting? Now, it's sort of interesting to see, but really, we still just follow our same basic rules. The conclusion's false in this row. Are all the premises true? No. Great. So then we haven't found invalidity. Let's move on to the next row. Last row, row 8. Conclusion's false. 2 premises are true, premise 1 and premise 2, but premise 3 is false. So, right, this argument is valid. Every row where the conclusion is false, and that's rows 2, 4, 6, and 8, at least one premise is always false. And then we can even specify, right? We say, we can say it's P2 in row 2, what here? P1 in row 4, P1 through P3, row 6, and P3 in row 8. Look at that. We're done. This is a valid argument. Why? Because every time the conclusion was false, at least one premise was false as well. So I hope you're starting to see here, it really doesn't matter what argument we get, so long as it's made up of the right components. It has simple statements as a basis, right, as the statement letters. It's constructed with our operators. All the statements, right, all the complex statements and simple statements, they're all well-formed formulas. They all follow the syntactical rules that we need to follow in the system. We can check that argument on a truth table and determine whether or not it's valid or invalid with complete accuracy, so long as we didn't make a mistake along the way. Speaking of well-formed formulas, and the rules of syntax. Let's do a few examples that have some brackets in them to help see how that works. So now, here's another two-premise argument. This time, the first premise is an implication statement, but the antecedent of that statement is a complex statement itself, either P or Q. So our antecedent is either P or Q, so if P or Q or both of them are true, then R must be true as well. Premise 2 is R. The conclusion is P. Will this be a valid argument? Let's take a look. So we need to construct a table as usual. How many letters do we have? P, Q, R. We've got R, we've got P. So we've got 3 again. 3 simple statements. P, Q, R. How many complex statements? Well, it's only the first premise that has a complex statement. And of course, it has the if P or Q, then R. Now, the if P or Q, or P or Q, right? Just that on its own is a complex statement, so it needs its own column. Now, I haven't put it in brackets here. I could. There's really no difference if you're just writing it on its own. There's no difference between putting it in brackets, P or Q, or leaving it out of the brackets. When we put our other column for P or Q, right, if P or Q, then R. Now, this time we need the brackets. Why? Well, what if we delete them? P or Q, then R. How do we read that, right? Because it's going to mean 2 different things, because of course we have 2 binary operators, so we have to specify what each of them is connecting. If we put the brackets here, we would then have, altogether it would be a disjunction, right? Because there's the disjunction outside of the brackets. And what would it be connecting as disjuncts? P or if Q, then R would be the second disjunct. So here the brackets matter because we've got 2 binary operators. So we need to make sure we get those right and that they're representing what the premises actually asserted. Okay, so we've got our columns done. Let's go ahead and stick in our premises and our conclusion. We'll identify those. Now we need to add our rows. Again, we've got 3 statement letters, so it's going to be 8 rows. 1, 2, 3, 4, 5, 6, 7, 8. And just as a tip, and I'll put in some other color here. Oh, let's make it gray. Generally speaking, for the final exam, you're going to be making tables, long tables. Generally speaking, I'm not making this as a promise. They're probably going to have 2, 3, or maybe 4 simple statements in them. So you're going to have 4, 8, or 16 rows to deal with. I'm not promising there won't be something that will require 32 rows, but I will refrain from asking you to do 64 or 128 or even more rows. Because if you can do these shorter tables, you can do longer ones. They just take more time and energy. So here again, same thing as before. So we've got our header row, we've got a column for every simple and complex statement, right? Including complex statements that are parts of even more complex statements. We've got the right number of rows, we've got our premises and conclusions labeled, so we have to fill in the truth values for the simple statements. I'll start with the method 2 this time. We'll start on the rightmost simple statement column, so R, so true, false, true, false, true, false, true, false. Move 1 to the left, double the number of trues and falses we enter at a time, so true, true, false, false, true, true, false, false. And then we're into the leftmost column, double the number of trues and falses at a time again, so true, 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 false, 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 false. Right, we did 1 at a time in this column, 2 at a time in this column, 4 at a time in this column. If we had even another column, we'd do 8 at a time. All right, now let's fill in the truth values for the complex statements of P or Q. To do that, we just look over to the rows in the P or Q column. I'm just gonna do it now. I'm not gonna talk through it as I have been before, in part for the sake of time and for the sake of my voice. So we're really only looking for a situation where both P and Q are false In that situation, the disjunction is false. So let's just look through. So true, 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 false, false. It's only in these last two rows that they're both false, so it's only in those two rows P or Q is false. Now, for the complex statement, if P or Q, then R. This time, our antecedent is the complex statement P or Q, so this is our antecedent row. All right. R is the consequent, so that's the consequent row. So what we're looking for are instances where P or Q is true, but R is false. It's only when we find that this complex statement, if either P or Q, then R, is false. So we'll just work through it. So in the first one, they're both the antecedent and consequent are true, so this is true. Second row, the implication statement's false. Our antecedent is true, and our consequent is false. So it's false, then they're both true again. We've got, well, it's false, right? Antecedent's true, consequent's false. They're both true. Oh, it's false again, right? Then it's true because the antecedent's false, and it's true. Like I was saying in a previous video, there are patterns you can detect, but it's not always worth learning them, particularly when you're first learning this, because the patterns can get a little bit weird. So in this instance, our implication statement, which usually, if you're just dealing with simple statements, it's only false 1 out of 4 times. All of a sudden in this row, we've got true, false, we've got true, false, we've got true, false, right, true, true. We've got it false 3 times, 3 out of 8 times. Is there any particular good reason for it? Well, yes, if you learn enough about the patterns, but it's worth learning all of the essential material we're learning here, because then you've got everything you need to make the tables and then learn the patterns if you want to. Okay, so now to check the argument for validity, we identify our conclusion column, that's P. What rows is P false in? The last 4 rows. It's just a feature of being a simple statement, right? Our leftmost simple statement column. So those are the only 4 we're interested in. I'll go row by row again. Look at that. This row right here, row 5, the very first row where our conclusion is false, all 3 premises are true. Boom, invalidity. This is an invalid argument. In fact, this is a version of a sort of popular, fallacious, invalid argument structure. You say, if A, then B, B, so A. It's not how it works, right? The implication statement is telling us if the antecedent is true, the consequent is true. So just pointing to the consequent as being true doesn't tell you the antecedent is true, right? If we say if it's raining, then it's cloudy. It's cloudy, so it must be raining. No, we said if it's raining, then it must be cloudy. That is, it can only rain if it's cloudy. But that doesn't mean that anytime it's cloudy, that it has to be raining. Or any other similar sort of pattern. Of course, in this case, we had a disjunction as the antecedent instead. Same basic reasoning applies, though. We're saying, look, to move the cursor, either have to hit the keyboard, touch a button on the keyboard, or click on the mouse, right? If either I press the cursor buttons on the keyboard or left click the mouse, then the cursor will move, right? That's true, but there might also be other ways of moving the cursor, say hitting the space bar. That moves the cursor. So just because the cursor moved doesn't necessarily mean I hit one of the keyboard buttons like the left or the right movement buttons, or I click the mouse. Just ways of filling this in, trying to bring it back to reality. Okay, so we know row 5 shows us invalidity. What about the other rows? Let's check those just for completeness, right? Like to completely check all of the rows. That's really what I mean there. So row 6, well, that row doesn't show us invalidity, right? Because at least one premise is false, while the conclusion is false. All right. Same with that row, and then in the 8th row, we actually have 2 false premises while the conclusion is false. All right. Look at that, and we're done. So in row 5, the conclusion is false, but all the premises are true, so it's an invalid argument. When you're doing questions on the exam or the last homework assignment, this is what we're going to be looking for. Now, of course, if you're doing the homework assignment, you have to have the natural language part that you're then translating into simple statements and then symbolizing those with the operators to get to our symbolic argument form like what we have here. So there is that extra step. Now I've got 2 more examples. I know I'm basically out of time here in terms of how long the video should be. I've got 2 more examples. I still want to work through those just to give you a little bit more content. This time I'm just going to do it. So instead of talking my way through this whole thing, right, and explaining all the bits and pieces, I'm just going to do it. That'll accelerate this process and make it a little bit quicker. You can see a few more examples here. Try to make sense of what I'm doing on your own. And so look, it's going to be all the same steps. So I've got the symbolic argument. This time I've got an implication statement, right? But now the consequent is a conjunction. I've got a couple negations here. I need to do all the same things. How many columns do I need? Well, how many letters do I have? Just start with that question. I've got 3 letters again. Look at that, 3 letters. I seem to, oh, I don't want that there. Seem to really be putting together examples with 3 letters. Right? So I've got 3 simple statements. Then I need extra columns for all the complex statements. What else do I have? And then O. Also O. I'm going to need a lot of columns, right? Because what do we have? We've got not E, we've got not U. I've got O, O and E. And of course, the implication. Label our premises and conclusion. Of course, we've got 3 simple statements. So again, just 8 rows. Shading, just for pizzazz. We fill in our simple statement truth values. Of course, our negation truth values. Our conjunction, we've got O and E, so it's these 2 columns we're interested in. And then finally, the implication, which is going to take U as the antecedent column and O and E as the consequent. So we have true, false, 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 true, 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 true. Okay, now I need to check the argument for validity or invalidity. I'm not going to highlight it this time. You don't have to. So on the homework assignment, on the exam, you don't have to do that. What you do have to do is specify whether or not the argument is valid or invalid. Right? The argument will be valid if there's always a false premise. It will be invalid if you can identify a row where the conclusion is false but all the premises are true. You have to specify what row or rows demonstrate invalidity if you find it. So let me just take a look here. So I only have 2 premises. Even though I've got all these different columns, right? I've got quite a bit of information on this table. Where is the conclusion false? Actually, just these first 4 rows. So those are the only ones I'm interested in. Now just looking through them. Okay, row 1, premise 2 is false. That doesn't show me invalidity. Row 2, premise 2 is false again. Row 3, premise 1 is false. Row 4, premise 1 is false again. So this is actually a valid argument, right? Well, I'm making typos on camera. In each row where the conclusion is false, at least one premise is always false. Look at that. Great, that's it, we're done. We could, of course, specify which premises are false in which rows, but this really tells us what we need to know. Let's move on to the last example. Oh, this one's a bit monstrous. Right? So, and look, I now have what? X, Y, O, and B. I've got 4 simple statement letters. So I'm going to need more rows this time. So this is going to be a bigger, more complex table. I've also got a, well, shouldn't be brackets around that B at all. We've got a biconditional in the first premise that connects B, right? B is one part of it. The other logical unit being connected is this complex statement, which overall, right, is a conjunction. That's what's going on within the parentheses, right, the round brackets. One of the conjuncts is another complex statement. So I have a disjunction embedded within a conjunction, embedded within a biconditional. Our second premise is then an implication statement. Our third premise is a simple statement, and the conclusion is a simple statement as well. All right. Now, this is more complicated and larger than any of the things we were just looking at. We just follow the same rules. There's really nothing new here. What's new? I've got 4 simple statements instead of 3. So look, I'll just put them in the order that I see them in the very first column. Well, I don't want that yet. How many extra columns do I need? Well, I need 1 for every complex statement, even the ones that are making up other ones. So I've got not X shows up in there. I've got Y or O. I've got not X and Y or O, and then I've got the biconditional statement. So let's stick all that in right now. I've got not X. I've got Y or O. I've got not X and Y or O. And one thing to note, even though I've changed what kind of bracket I'm using a square one there for Y or O and a round one here. We're just switching between round and square if we've got more than one set, just to help show where the difference is. There's no difference between using the square brackets here for Y or O in the premise and switching them back to round brackets. But those both mean the same thing. I've used square brackets in the text just to help show where they start and stop. Because if you've got something like this, right, it's a little bit easier to get confused about what the bracket is closing off, right? Especially if you've got brackets within brackets within brackets. So it doesn't matter if they're round or square, right? What's really important is that if you've got a square bracket that opens somewhere, right, like there, it closes somewhere else. When you've got a round bracket that opens somewhere, right, this whole expression that it closes somewhere else. Whenever they open, they also have to close, and they need to be in the right sorts of places to produce a well-formed formula. And then, so up here, not X and Y or O. And then I'm just going to copy and paste my biconditional symbol rather than sticking it in as a symbol. One handy trick in Word, if you just double click on a box like this, Word will try to reformat it so it's the right size. Okay, so we've got all this now. Oh boy, that's a lot of columns. Okay, the truth table can get complex. It doesn't matter how much stuff is there. I know what to do. Now I need to figure out how many rows. This time I've got 4 simple statements. So we've been dealing with 8 rows. Now I've got 16. 2 to the power of n, and is 4 is 16. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Go ahead and put a little bit of coloring up here just to make it look pretty. Why don't we go with, sure, go with that. That's hard to read. I don't like that after all. Go back to the blue, light blue. Okay, I got 16 rows now. I've got a pretty big table. I'm going to shrink down my own appearance here. Look, it's the same thing. I need to fill in half true and half false in the first column for the simple statement. Or I could start at the last one and alternate. But so look, same thing. So it's going to be half true, half false. In this case, it's going to be 8 true, 8 false. So 8 true, 8 false. Move one column over to the right, have the number at a time that I enter, make sure to fill the column. So I entered 8 and 8. Now it's going to be 4 and 4, and then 4 and 4 again. So there. Same thing, move over. So instead of 4 and 4, it's 2 at a time. So true, true, false, false. No. And then finally, we've got our last simple statement, so we just alternate. Look at that. We filled in our simple statement truth values. And here again, what do we have? Very first row, they're all true. Very last row, they're all false. And every single row in between is a different combination of them being true or false. That's really all this is. And you can look through, and if you just look through row by row, you'll see that each row represents a different combination of those true-false values, and there are no combinations of true and false for those 4 things that isn't represented in these 16 rows. Okay, not X. To figure that out, I just look back to the X column, and that was my first one. It's half true and half false, so this is just the opposite, so half false, half true. Y or O. I need to look to these 2 columns. That complex statement, Y or O, it's only false when they're both false, so that's really all I'm looking for. As long as at least one of them is true, it's true as well. I'm just going to work through that without really talking it out. There we go. And again, we've got, it's just simple statements. That a disjunction like that's only false 1 out of 4 times. So on our table out of 16, how many falses are we going to have? 4, right? 1 out of 4. That's 4 out of 16. Okay, now this more complex statement, this conjunction, not X and Y or O. So that's only true when both not X is true, right? And when Y or O is true. That's the only time the conjunction is true. So I need to look through each of these columns, check the rows. My complex statement in this column is only true when both of these are true. So I'm just going to work through that. Again, I'm not going to talk it out. I'll just do it. There. It's only true in those rows. In all the other rows, at least one of them's false, so the conjunction's false. But in these rows, conjunction is true because both values are true. So now we got to go to our last row. It's that biconditional. And what's the biconditional connecting? Well, that complex statement we just filled in, this is one part of our biconditional. B is the other part. And so what the biconditional tells us is that they're both true or both false at the same time. Right? It's just not true that one's true and the other one's false. They're both true or both false. Biconditional is true so long as that's the case. They're both true or false. So that's all I'm looking for. Right? So look, in this first row, one's true, the other one's false. So the biconditional is false. Second row, right? B is false. The conjunction's false. They're both false, so the biconditional is true. That's all we're looking for. So look, here again, they're mixed, so it's false. Not mixed, true. Mixed, false. Not mixed, true. Mixed, false. Not mixed, true. Not mixed, mixed. Not mixed. Mixed. Not mixed. Mixed and not, right? And now here, what's the pattern? I don't know. I honestly, when I said there are patterns to be learned, there are, but we got into a spot where the pattern that would sort of govern how many trues and falses we should expect here, that pattern's so complicated. I don't know it off the top of my head, but I know how to fill in the truth values for that complex statement, so I don't need to know the pattern. All right, last bit. I'm sort of well over time now, my apologies, but hopefully having this extra content is helpful. Now I need to take a look at all the rows that are the conclusion. Oh, and see, I forgot to do that. Silly me, I forgot to identify the rows, or the columns that are my premises and my conclusion. I can just add that in now. I should have done it earlier. Oh. I've also just realized, and this, I'm a little bit embarrassed, I completely left out a premise here, right? If O, then not X. I'm just going to go ahead and put that in. Right now, this has sort of kicked things off my page for me. I've just sort of dragged it back. If O, then not X. Look at that. I completely forgot about this. Just going to add it in now. What do I need to look at? I need to look at the column for O and the column for not X. So let's fill in those values now. So the first row, implication's false because our antecedent is true and the consequence false. There. All right, I've added it back in. Whew. Save myself. All right, and so we've got it. I've got the conclusion column marked. I've got premise 3, premise 2, premise 1. Look at that. So now all I have to do is go through and check all the different rows to see if I ever have the conclusion false while the premises are true. And now this time I'm going to use the highlighter tool here. And I'm just going to highlight in red because now there's a lot of information on this truth table. It's a little hard to keep track of everything and you know, keep my eyes focused. So let's see. I see false conclusion, false conclusion, false, 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 false. So the conclusion is false in half the rows. I've got 8 rows to check. True, there's a false premise, so that's fine. Here's a false premise. There's a false premise. There's a false premise. Turn on the highlighter again. False. See what I'm going through? I'm just going through, and because I've got such a big table and everything's spread out, I've identified where the conclusion's false here. And as long as I find one false premise, right, each of these rows, I know the row doesn't show me invalidity. So I'm not even bothering with premise 1 in these first handful of rows. Why? Because premise 2 and premise 3 are just closer to the conclusion on my table. And as long as I see at least one of them false, I don't care if premise 1 is true or false. So I've got false premises in rows 2, 4, 6, and 8. When I get to row 10, though, both of those premises are true. So now I go over, yep, premise 1 is false, so I still have a valid argument, at least so far. I haven't seen invalidity. And in this row, I've got a false premise over here. Premise 3 and premise 2 are true in this row 14. So I'm going to go back over to premise 1. And then I've got false premise down row 16. So look at that. I have another valid argument. In every row where the conclusion is false, I've identified at least one false premise. And so this argument is valid. I go making typos again. How embarrassing. What a terrible way to end this video. This argument is valid. Every row where the conclusion was 2, 4, 6, 8, 10, and 10, 12, 14, and 16, at least one premise is false. 2, 4, 6, 8, 10, 12, 14, and 16. There we go. So I'm done. I'll zoom out a little bit so you can sort of see this whole thing. So we've got this more complex argument. Right, we've got a big truth table, but it still has all the same components. We've got our simple statements. We've got columns to represent each complex statement. Right? We try to make them more complex as we go to the right. This is our most complex statement, so it's the furthest to the right. This complex statement makes use of our other complex statement columns, right? The column for not X, the column for Y or O. We've also got if O, then not X here, right? Which also has to use the not X column. So we've tried to increase the complexity as we go to the right. Now, between these two columns, the implication and the disjunction, it doesn't really matter what order they come in. They're sort of interchangeable. They don't really rely on each other. They both rely on contents earlier in our table, so that's fine. And then once we constructed the whole table, we filled in all of our simple statement truth values. We filled in all of our complex statement truth values after. We then go through our conclusion row, identify every row where the conclusion is false, check to see if at least one premise is false. And in every instance, we had at least one false premise, so this is a valid argument. And it doesn't matter if we had 128 rows, we would just do the same thing. Of course, it gets a little bit unwieldy and a little bit difficult, so I'm not going to make you do that. You might have to do something this complex, say in the final. This is also, because of how complex this can get, this is one good reason to try to stick to a fairly simple argument for the last homework assignment. Try to get something that only has 2 or 3 or maybe 4 simple statements, preferably a fairly simple argument pattern. I try to avoid something like this, you know, not X and Y or O if and only if B. And then an implication thrown in there. Try to keep it fairly simple. An operator, maybe a couple operators, a very small handful of simple statements. Try to just stick with something like that. So I hope this has been helpful. I hope this has helped demonstrate just how to put what we've been learning into practice using some more examples. try those practice questions, particularly at the end of chapter 5 now. If you've got questions, things aren't making sense, try to go back and look at the videos, look at the text. Feel free to get a hold of me if you want to ask me some questions. Also keep in mind that you can access the Philosophy Help Center online Thursday afternoons. It's running virtually now. If you've got the Zoom program, which everybody at Lethbridge is now supposed to have access to, you can join that Zoom meeting and talk to the tutors there in the Philosophy Help Center, and they can help you work through some of this material if you want and try to help answer some of the questions you might have. So that's all I have for today. I hope this has been helpful, and I hope you're all doing well. I'll be back next week when we're going to take a look at the short truth table method, which gives us an easier way of trying to accomplish what we've done here. So I hope you're all well. Have an excellent weekend, and I'll see you next week. Bye for now.